Hello friends, welcome back to another video. Today I'd like to talk about algebras. So, what is an algebra? So an algebra is a vector space which we'll denote by A over a field K, so maybe the complex numbers, maybe the integers, right? With a map, let's call it mu, which takes you to the direct product of two copies of it to 1, the multiplication map. Yeah, this is probably going to be covered by me, huh? So a map mu called the multiplication. Okay, so the algebra, or well, let's say A is unital if there exists one A in A such that mu 1A A is equal to mu A 1A is equal to A for all A in A. So this is the identity for the multiplication operator, right? You may think of this as 1A times A equals A, and the same for the other side. And A is associative if mu of A, B, C is mu of A, mu BC for all ABC in A. Okay, so we know what unital and associative means. Again, I can write here A times B times C is equal to A times B times C. Indeed, like we can denote this multiplication operator by a dot, in which case this is true. But we needn't do this necessarily. Okay. Now we have that. Let's look at some examples, maybe. I guess example. So let's take the algebra of 2x2 matrices. So I'll denote this by M2 over R, let's say. So, for example, you'd write a matrix like this to be an element of M2R. Maybe I'll call it like this. And let's call this X. So then X prime would be, we would define this map mu, which sends A cross A to A, and sends X prime to X prime as multiplied as matrices, of course, in the usual sense, right? And then the rest. Okay. And this you could then verify that is also in M2R, of course, because the size didn't change and the field didn't change, so everything's good. Who's the identity? Well, the identity is just the 2x2 matrix like this. And the is it associative, right? So now I've shown that it's unital. Is it associative? So one, I believe, would have to check this in the tedious sense, yes. So you would have to perform this calculation tediously and show that it is indeed associative, unfortunately. So you'd have to do x prime, x second, of course, we know that matrix multiplication is associative, but it would be nice to verify. Okay, let's do another more interesting example. So one can make a vector space. So let's have a group G, finite group. Well, the size of G is finite. And then we can make a vector space KG, which is the group algebra of G. And the group algebra is just a vector space spanned by the elements of G. So it's the span over K of elements G in G. So for example, let's say sub-example, let's say that G is the cyclic group of order 2. I think I have a video on groups in case you need a refresher. So let's say this is the group, right? And then KG, let's say RG, make this very much an example. RG would be, a typical element of RG would be something like x1e plus x2a plus x3a squared. So you force linear independence of all these group elements. And I'm claim KG, or let's do RG first. Let's call this actually Z2, right? The cyclic group of order 2. So Z2. Claim RZ2 is an algebra. So perhaps the name already gives it away, right? It's called a group algebra in the generic case, but let's prove it, right? Proof. In fact, I'll say more, is an associative unital algebra. Okay, proof. So we should have that there exists a multiplication map, right? Technically, I should say here with what multiplication map, but I want to make it pedagogical in that I'm introducing the multiplication map to make it an algebra, right? So with the multiplication on G, right? With multiplication on G, we have for, let's say, x prime in RZ2, we'd have x prime be, like this would be the general element, this would be x, this would be x prime, and now the way that we multiply is we use regular multiplication on the field, in which case the xi's and xi primes are in R. And then we multiply the group elements, right? So E times E will give E. I can do the other ones in my head. So for example, it'll give me x1, x2 prime A. And it'll give me also x2, x1 prime A. Will give me any more A's? It will, right? Because of A squared with A squared. So in the cyclic group, A squared times A squared is A. So I'll add another element into A. x3 prime A. Who will be in A squared? So in A squared, I'll have E times A squared, which will be x1, x3 prime, plus x1, x3, x1 prime. And then I'll have the A's with the A squareds. So I'll have plus x2, x3, no, the A's with the A's, yeah, x2, x2 prime, A squared. And then there's another E element, so let's add that in. So there's x1 prime, and then there's x2, x3 prime, and x3, x2 prime. Okay, that's 9, and it makes sense that there's 9 of them. So is this in RZ2? Well, of course, it's in RZ2 because you can see all of them are spanned by the basis. So just because the group multiplication is closed, it'll follow that the algebra is, no, that the vector space is an algebra. Okay, is it associative? So algebra, yes. Okay, is it associative? So for associativity, for example, it would be enough to check this for the basis. So K, well, everything I'm saying is going to be general, but let's say it like this. So RZ2 has basis, A squared. So it's enough to check associativity. So check associativity on basis. But of course, the group multiplication is associative, right? So, yeah, hence associative. Okay, unital, again, E is the unit. This is obvious. So x times E would be x1 E times E plus x2 E, A times E plus x3 A squared times E. And again, by the way the identity works on groups, and you can verify that this is x, and also like this. So unital. Okay, and indeed this extends much the same way to kg for any field k and any finite group g. Cool. And I want to introduce Frobenius algebras as a last example. So example 3, Frobenius algebra. So Frobenius algebras have an extra structure on them. So which structure shall we use? Let beta, which takes AA, the algebra, right? Frobenius algebras. So let B, which takes AA to K to the field, be a non-degenerate pairing. What's a pairing? A pairing is just bilinear form, which takes i.e. Pairing means that beta of let's say C1a C2b is C1 C2 beta AB for C1 C2 in K, A B in A. Okay, that's a pairing. And non-degenerate means that if beta AB equals 0 for all B and A, then A equals 0. Okay, so just like with matrices, for example, when you say something is degenerate, this is what you mean. Okay, so beta is non-degenerate means that it can only be 0 when one of the entries is 0, at least. So a Frobenius algebra is an algebra with this sort of structure. So let's ask the question, what do we need? So what do we need? Need to make Kg a Frobenius algebra? Well, we need to define beta. Yeah, okay, I perhaps here I should say then A is a Frobenius algebra. Okay. So what do we need to make Kg a Frobenius algebra? We need to introduce such a bilinear pairing, or bilinear form. We need to introduce this sort of beta. Well, can I show you this sufficiently generally? No, I think there are many different choices one can make, unfortunately. Let's look at the polynomial ring, actually. So, sub-example, a polynomial ring over T, quotiented by T squared minus 1. So what do I mean by this? By the ideal generated by T squared minus 1. So what do I mean by this? KT is the span over K, the field, of 1, T squared, no. So the polynomial ring goes up to infinity, okay? And then this space, A, is this space KT, but with the added relation that wherever you see T squared, you replace it by a 1, okay? So then A is just the span over K of 1 and T, okay? So T squared is 1. So it's essentially Z2, right? So this is actually K Z 2. By the way, I had Z2 written there, but it's Z3, obviously. It's the cyclic group of order 3. I'm not going to correct it everywhere, but everywhere it should be Z3. Cyclic group of order 3. This one is a cyclic group of order 2. And some element x in A would then be written as x1, 1. We can suppress this one, plus x2t. And that's it. So a choice of pairing would be, for example, b11 equals 1, b1t equals bt1 equals 0, and btt equals 1, right? So written as a matrix in this basis, beta would be this. And it's clearly non-degenerate because, yeah, well, it's just when is a matrix degenerate, right? When its determinant is 0, well, I have the determinant of this equals 1, so not 0, not degenerate. Okay, yeah, so that's an example of a Frobenius algebra. And I'll show you in the next video why this is interesting, why we might want to look at Frobenius algebras. Okay, cool. Thanks for watching. Bye-bye.